Okay, people, welcome to Let's Get to the Marks. We're looking at GCSE Combined Science, the trilogy, and this is physics paper one, and it's from 2023. Now, is this just useful for people doing combined science? No, of course not. People who are studying the separate physics GCSE, everything within the combined science papers you need to know for your GCSE physics exam as well. So this is perfect practice for you. You can't get better than exam questions written by the exam board. And so if you have done all the past papers available to you for separate physics, you need to hit the combined science ones because they may take questions from the combined science ones and ask very similar ones in the physics GCSE that they haven't asked yet. So you might find certain topics that have never come up in the physics past papers that come up in the combined science and vice versa. If you're a combined scientist, it's good to look, if you've done all the combined science papers, it's good to look at the physics GCSE papers. You may find that there are questions that come up in the physics GCSE papers that are part of your content that have never come up in a combined science. So without further ado, let's get into it. So you normally have about 70 minutes to do one of these. We're going to whip through. I recommend that you pause the video. I'm not going to say it at the start of each question, but try to pause the video, grab a scrap bit of paper and a pen, have a go at the question, and then unpause the video and see if you got the right answer. Even if it's a 6 marker, just try to put down the key words or key points you would put. It helps you actively revise. All right, let's get into it. Question 1.1. Which of the following is a renewable energy resource? Of course, the stem of the question says wind power and solar power are both renewable energy resources used to generate electricity for the national grid. Now, for 1 mark, which of these following three is a renewable resource? Geothermal, natural gas, nuclear fuel. A renewable resource is one that's not going to run out in human species lifetime. So that is going to be geothermal. Beneath our feet are hot rocks created by radioactive processes in the Earth's core. And these generate heat that we can tap into. We pour water down tubes that we drill into the ground, and that water turns to steam. It turns a big wheel called a turbine, which generates electricity. Only really in certain locations in the earth is it a viable method for generating electricity, such as New Zealand or Iceland, where you've got hot rocks close to the surface. Natural gas, of course, is a fossil fuel made from the dead bodies of marine animals and plants and all of that business. And that natural gas is going to run out. And nuclear fuel theoretically could run out as well. So it's a non-renewable resource. Okay, let's move on because if I waffle like that, this exam paper is going to take 50 hours to get done. Right. 1.2. The energy transfer by the national grid in 1 second was 36 gigajoules. Big capital G tells you it's a big number, gigajoules. Which of the following is the same as 36 gigajoules? So this is where if you use your computer and your phone and you're downloading stuff all the time, you'll have an idea of the size of the different things. So kilo means 1,000. You think of 1,000 kilobytes. Mega means a million, so that is going to be 6 zeros. Yikes. Bum bum. Then we have giga. You think of gigabytes. If you're downloading movies and things, you need a bit more memory. So giga is a billion, and then you have tera, which is a trillion. So you've got 12 zeros. So which one of these represents 36 giga? So it's going to be the one with 36 in front of it and 9 zeros after it because it's basically 36 billion and giga stands for a billion. So gigajoules, 36 billion joules. That's quite a lot of energy generated by the national grid in 1 second. Wow. Okay. Zing, zing, zing. We're on 1.3. And straight away, we're into a graph analysis. So 1.3, figure one shows the mean power output from solar and wind energy resources in the UK and how it varied between 2014 and 2019. Now we've got wind power by the light grey bars, solar power by the little dark grey bars. We've got the mean power output, how much power is being produced in megawatts on the side. And we've got the years that these were measured in. Okay, that's figure one. Let's check out figure two. Figure two shows the power output from solar and wind energy resources and how it varies just across the months of 1 year, the mean variation over 1 year. So we've got the power output again on the left. The dashed line down here represents solar, and the solid black line represents wind. Let's go and look at the question. I sense that, yes, a 6 marker. So this 6 marker says, explain the changes in the power output from solar and wind energy resources between 2014 and 19. You should include an explanation of the change in power output during a typical year as well. So they want us to use both figure 1 and figure 2. Now, this is really cool because what this does, and you'll notice this with most 6 markers, they give you an idea of how to plan your answer. So they want us to talk about the first graph, which showed from 2014 to 19. And then they want us to talk about the second graph, which showed us within 1 year in particular. So you could almost say, well, maybe I'll get 3 marks for that and 3 for that. Or you might find it's like 4 and 2. You don't want to do 5 and 1. You don't want to just make one comment about one thing they've asked. So I'd go for 4 about the first, 2 about the second, or 3 and 3, and get your 6 marks. Right, I'm going to write this answer up by the graphs so that we can talk through it. So let's do the first part of the answer. Figure 1 shows how the mean power output from solar and wind energy resources in the UK varied between 2014 and 19. They want us to talk about what's going on with these. So we're just going to explain and evaluate this. So let's start with one of these. Let's check out solar power. It looks like solar power increased from 2014 to 16, and then it carried on a slight increase to 2019. I can make a definite statement there and say solar power increased slightly between 2014 and 2019. What's the reason why we might have generated more electricity from solar power? Use any sensible suggestion. More people have solar panels every year, something like that. Like, so people are buying more solar panels, or because of global warming, there is greater intensity of sunlight. So we're getting more sun because of global warming, more heat for those solar panels. And I can't explain, I can't spell. Okay, we all know that. Right, so that will possibly get you 2 marks. You've said what's happened to solar power, and then you've followed it up with a reasonable explanation of why. Now let's check out wind power, because we can probably get 4 marks here just from talking about this stuff. So we can see, look, wind power goes up 2014 to 15, then it drops temporarily to 2016, and then continues on its way up to 2019. So that's going to get us a mark for explaining that trend. So I'm going to type that up here. So wind power increased 2015 to 2016. I mean, really, I want to say the mean power output generated by wind power, but that's just long for me. Wind power increased 2015 to 2000. Oops, sorry, got all my dates wrong. 2014 to 2015 was the increase, then went down in 2016. I'm going to give an explanation because it used the word explain in the stem of the question. So I'm going to say possibly because it was less windy that year. So it just might have been an anomaly and there was slightly less wind that year. You know, maybe some of the turbines broke and needed repair that year. Who knows? Or less investment in wind turbines that year. We don't know. It then increased, yikes, between 2016 and 2019. So again, we increased, maybe more turbines were built. So more wind turbines built, or it got windier. It may be that they located more of the wind turbines on the coast where there's more wind. Could all sorts of things. So again, we've described a trend here, and then we've given a possible an explanation for it. This should smash you 4 marks. Let's move down and look at the second figure and see if we can grab 2 more marks. I'm sure we can get at least 3 marks out of the next figure. All right. So that's your notes there. Now try again. Make sure you try to pause the video and all that business as we zing on to each of these questions. So now this is the rest of the 6 marker, and you've got figure 2 shows how power output from solar and wind varies in a typical year. What can we say about the black line, the wind power compared to the solar? I'd make a statement about that straight away. What can you spot? Generally, or for most of the year, wind power generates more electricity or more power um, than solar power. So that's just a general statement. Why UK is windier than it is sunny. Okay, that's a bit of a rubbish explanation, but let's look for some more points we can make. Wind power is higher in the winter and lower in the summer. This is because it is windier in the winter. So it's windier in the winter, or there's less wind in the summer, and that explains why the wind power ducks down there. Now let's check out what we can say about the solar power. Solar power is higher than wind power in the summer. So why do we think solar power is greater than the power generated by wind for the months of that would be June and July only? But why? This is because um, there is greater light intensity. Basically, there's a higher strength of light. Also, longer daylight hours. So we would also expect there's longer daylight hours, whereas in winter, less daylight hours, so less solar power. There's also less sun intensity, but I've run out of room. So it's not just that the sun is weaker or that the sunlight, we get less sunlight getting to us, but there's also less time for that sunlight to get to us in the winter because we have less daylight hours. Okay, that is definitely going to smash you another 3 or 4 marks. Okay, and you only need 6. So boom, let's move on. Don't forget, guys, hit the like button. It helps out the channel, it helps out the YouTube algorithm, get this content to other people. We're on question 2 now of this combined science physics paper for 2023. Body analysis scales use electrical resistance of a person's legs to estimate the percentage of water in their body. Body analysis, figure 3 shows the body analysis scales. So here we got the scales, person steps on, we get a circuit complete, and we get a reading. The person's legs contain solid tissue and water. A student used resistors to model both the solid tissue and the water. The student connected a 20 ohm resistor in parallel with resistor R. So my key word here, guys, which they've told us, is in parallel. And this is where you're probably going to need to know your circuit rules for parallel and series circuits to do a potential difference in current. And this shows the diagram. So we've got these two in parallel. Lovely jubbly. What's this first question? To determine the total resistance of both resistors, a voltmeter must be connected in the circuit, blah, blah, blah. Basically, they want us to connect a voltmeter. How would we measure the voltage? Well, we just need to connect it in parallel. So we can connect the voltmeter around any of these resistors, and you can do it either way, and you'll get the mark. Cool. Now, let's read the rest of the question. Okay, yikes. 2.2, the student calculated the total resistance of the 2 resistors. The student's answer was 26. Explain why the student cannot be correct. So, what the student is thinking, he says, let's get rid of those. What the student is thinking is that if this is 20 ohms, then this is 6 ohms. Now, there's a reason in a parallel circuit that this is incorrect, sorry. There's a rule for parallel circuits, and the rule for parallel circuits is that the total resistance in any parallel circuit must be lower than the smallest resistor. Now, we don't know whether R is 19 ohms or 21 ohms. We don't know whether it's smaller or bigger than 20. But what we do know is that the total resistance must be less than 20. It has to be less than any of the individual resistors. And we know there's 20 ohms through one resistor. The total resistance must be less. You don't have to know why. There's an equation 1 over T is equal to 1 over R plus 1 over R2. And that explains, if you carry out that equation, you'll find out why the total resistance in parallel circuits is always lower than the lowest of the resistors. But yeah, that's the reason. So the student is definitely wrong. So you need to know this rule off by heart. If you don't know it, grab a revision card, make a note of this. So total resistance in a parallel circuit must be lower than the smallest individual resistor. So if you have two resistors and one is 5 ohms and one is 6 ohms and they're in parallel, then the total resistance has to be smaller than the smallest one. So it'd have to be less than 5, like 4 ohms or something. So total resistance in a parallel circuit must be lower than the smallest individual resistor. So it must be below, oh my gosh, I can't spell, below 20 ohms. And that's going to get you 2 wonderful marks. Right, let's zing on. So we're now on 2.3. Excuse me while I have some coffee. Beautiful. Write down the equation that links current resistance and potential difference. I guess you are super glad that you guys have an equation sheet, some lovely free marks. So you can write this. I always write V equals IR because I remember this when the days when you had to memorize it, very itchy rash. And so I write it out like that. There is a triangle, V over IR. You could represent this as I equals V over R or R equals V over I. Any relationship that's correct will get you the mark here. Now, next thing we have, when the total resistance of the resistors was 7.5, and the current was 480 milliamps, calculate the potential difference across the two resistors. And this is worth 3 marks. And it's beautiful because we've just done the equation. So it's plugged the numbers in. Now, if you do this, you're going to make a mistake, but obviously you can see I times R. So we're going to go 480, investigated how the resistance of R affected the total resistance of the circuit. We've got resistance of R in ohms, 5, 10, 15, 20, 25. The total resistance of the circuit like that. Some of the results are plotted in figure 5. We're going to have to plot a graph here, folks. Okay, so we've got a graph here and it says 2.5, complete figure 5. You should label both axes, 1 mark. Plot 2 remaining values from the table. So just plotting 2 points, 1 mark, and draw a line of best fit, 3 marks. Lovely, easy 3 marks here. Now, there's a rule. The first column in the table is the independent variable. This always goes on the horizontal or x-axis. The second column or last column in a table is the dependent variable, and that always goes on your vertical or your y-axis. So just label and copy that exactly onto the axes, okay? If you just say resistance of R, you won't get the marks. You must say the unit in ohms, total resistance of the circuit in ohms. So you have to actually put that stuff there. Right, let's get rid of these and let me put this over here. So we want to put here total resistance, excuse my crusty writing. And this is the key in ohms. You could use the symbol. And then this is, I'm not going to write the full thing out. You should, if you're doing this, resistance of R. And again, in ohms, you can use the symbol. You're allowed to do that in exams. Now that is going to get you 1 of the 3 marks. Now the next mark that was going here was for plotting the 2 values. So let's look, we're missing one at 15 and 20. Let's go up and check it out in the table. So 15 is 8.6 and 20 is 10. So we want 8.6 and 10. Let's zing back down. Now, at 15, I want 8.6. So this would be 9. That means that each of these squares, you've got 5 baby squares. So you do 1 because the value is 8 to 9 there is a 1. And you divide it by 5. Each square, 1 over 5. Each square is worth 0.2. So if I want to do 8.6, I want to come up to 8 and then add 0.2, 0.2, 0.2. That is 8.6. right there. And then for the 20, it's lovely jubbly, easy peasy pudding and pie because it's bang on 10. And then that will get us a second mark. And then they say the third mark is for a line of best fit. I want to draw a curve here. Notice there's a natural curve going on. So if you can get a natural curve going like that, it's fine. So you can do a curve of best fit like that, and that'll get us the next mark. Beautiful. Okay, let's zing on. Oi, oi, oi. What resistance R would give a total resistance of 4.4? So what resistance of R would give a total resistance of 4.4? Oh, we've got to use figure 5. I'm going to have to go back up to the graph and say what would give a resistance of 4.4. What I need to do is just stick me, oh dear, that is terrible, isn't it? Right, let's do this line here. Got off on a bit of a better start. All right, total resistance of 4.4. So we want to go 4 here. 4.4 is there. So 4 and then 0, 4.2, 4.4. We draw a line across, and then you would draw a line down, and then you'd have to work out what that number is there. So it looks like 5, but then we've got a different scale going on here. So each one of these is worth zero point 0.5. So that looks like 5, 6, you'd have 7, 8, 9, 10. So that looks like it's going to be 6. What resistance of R will give a total of 4.4? Be 6 ohms. And that makes sense because the resistance of R being an individual component must always be greater than the total resistance, and 6 is bigger than 4.4. All right, now let's zing down a little. The body analysis scales initially show a reading of 0. When the student steps onto the scales, the reading is 64.8. The student steps off the scales, then immediately steps back on. The scales now say 64.1. There is no reason why the scales should have a different reading. And it tells us that they were on 0.0. So it says complete the sentence. The difference between the two values by the scales is due to a something error. It can't be a 0 error, right? It can't be a 0 error as the scales read 0. So it's not a 0 error. 0 error is if it had said like 0.2. You go to weigh something and it's already measuring something, even though something's not on the scales. So you're going to get a incorrect result. So this is not 0 error because it was correct for it to be 0.0. So they're telling you it's not 0 error. So what type of error is it where you do two measurements? Is it systemic error? Is it systematic error? Is it an error with their method? No, they just stepped on the scales. They did exactly what they did the first time. So it's nothing to do with the method they're using. It is called a random error. So this, folks, is a random error. And that's any two measurements carried out in the exact same way are normally not exactly the same. And that's due to random error. Okay. 2.8. The height the student is programmed into the scales. So they put the student's height in the scales. The scales place the student in either category A, B, or C based on their height and mass. So we've got different categories here. Figure 6 shows how the scales use the category and the total resistance of the legs to determine the body water percentage. So using this category, we can work out the body water percentage. So if you're in category A and your resistance is 700, you'd follow the line up here to 700 and say, oh, this person has a 46% body water, something like that. So it's a way of calculating their body water percentage. Now, we've got the final part to this question is a 3 marker. The total resistance of the student's legs is 600 kilonewtons. Okay, that's 600. Sorry, not newtons. What am I on about? 600 kilo ohms, which is 600,000 ohms. A healthy body water percentage is between 45 and 65. So that is healthy. Anything below that or above that is going to be unhealthy. Different measurements of the mass of the student mean the student could be in either category A or B. Evaluate if the student has a healthy body percentage. What we need to do is go and look at the oh gosh, We need to go and look at 600 kilonewtons, which is here. What I'm going to do is draw a line up to A. And let's see what percentage body weight water do we get. So someone at A has 62. So they are 62%, somewhere like that. They're about 62%. Now, we were told that 45 to 65 was healthy. So if the person is in category A, they're healthy. Let's continue that line up and see what happens if they were category B. So if we continue the line up, we hit here, which is 68%. And so for B, they would be 68%. Now, remember, we were told that outside of 45 to 65 is unhealthy. So if they're in category B, they have 68%. This is beyond the healthy range, so they're unhealthy. So let's go write that all into our answer and zing back down. So what we want to say is um, if the person is category A, then they are healthy as they have body water percentage of 62, which is in the healthy range. So it was within the healthy range. However, if they are in category B, then they are unhealthy as their body water percentage, is 68, which is above the range, 45 to 65. Bosh. So that is 3 lovely jubbly marks, okay? And you'll always get a mark if you've messed up your answer in the writing, but you drew a line up from 600 kilo ohms and you drew a line across. So if you actually showed your lines on the graph, then that would definitely pick you up a working out mark. If you've got a good examiner and you've done this black line here and across, and you may have got the wrong percentage, you may have written the wrong answer, but if they see you're working out on the graph, you're likely to be awarded a mark, at least 1 out of 3, which is better than nothing. Right, we're on to the third question, talking of threes. So Figure 7 shows how the national grid transfers energy from a power station to some street lamps. Have a look at that graph. I'm just going to have a sip of coffee. Wunderbar. Right. We've got power station cables going to a transformer, up into cables being carried by these pylons, and then the cables come down to another transformer. You've probably seen these near your house, little green boxes with a lightning bolt sign on them. And then down to the street lamps on a street. Explain how Transformer X increases the efficiency of the national grid. So I'm just going to explain it, but if I was you, I'd pause the video, have a go. There are some keywords you can just memorize on a revision card for this. This question comes up a lot and is a very common question. So essentially, what type of transformer is this? It's a step-up transformer, so that's going to get you a mark. It increases the voltage. So just to explain so you know why we increase the voltage, I'm going to give you the explanation. So we produce about 40,000 volts in a power station, and we step that up to, let's just say, 400,000 volts. Why? Why are we sending volts to people's houses? We're not actually trying to get volts to people's houses. We're trying to get power there. If you look on the back of your kettle, your oven, they have a watt rating in power. The things you use in your house that are electrical use power. We need to get that power from the power station where they're burning coal or using sunlight or using a wind turbine. We need to get that miles away from your house to your house and deliver you that power. Now, P equals I times V. I don't need some stupid little line down there. What the hell was that? Okay. Oh, yeah, yeah, yeah. This is... Okay. Just about getting ready now. Okay, so 400,000, P equals I times V. So what is this all about? Well, think about it. If I want to get 400,000 watts to your house, let's say I want to get 400,000 watts to your street, I can do that in two ways. I could do like we've made 40,000 volts in the power station, so I could do 40,000 volts and I could do 10 amps. 10 times 40,000 is equal to 400,000. Beautiful. The only problem is current, okay, is produces heat. So current, you get resistance, you get something called the heating effect, and we're going to lose energy dissipated to the environment. So what we can do, still to deliver 400,000, I still want to get 400,000 watts to your house. I can do that by using 1 amp and increasing the voltage to 400,000. So by increasing the voltage, I can lower the current, get the same amount of power to your house without producing the heat that you get from a high current. So what do you need to write in your answer? And this is all you need to memorize for your answer. So we need to say X steps up voltage as a high voltage means we can use a low current, which reduces energy losses as heat to the environment or dissipated. It stops the same amount, and this is more efficient. So more efficient power transmission or energy transmission. So it's basically a more efficient way of getting the energy from one place to another is to use a high voltage and a low current. You still get the same power and you get it over there. If you have to send a high current over miles and miles of cables, they're going to heat up. You're going to lose a lot of that energy and you're going to lose a lot of that power. Okay, all of these numbers you didn't need. This was just me trying to explain to you why they step up the voltage. Of course, why an equivalent question, or sorry, not equivalent, but another very common question on the national grid is they'll ask you about transformer Y and they'll say, what is the purpose of transformer Y? It's normally only 2 marks. The idea behind transformer Y is to lower the voltage. Again, that allows us to increase current because you need current to operate all your appliances. But that's not the answer they're looking for. They want you to say why as a step down transformer lowers the voltage. This makes it safe because high voltages are dangerous, can cause electrocution. And that's the answer that they're really looking for here. All right, let's zing, zing. Okay, so we are here on the next questione. So the potential difference across the primary coil in transformer Y is 400,000 volts. The potential difference across the secondary coil is 11,000 volts. The current in the primary coil is 680 amps. Calculate the current in the secondary coil. So this is what a transformer looks like. It's an iron core and it has 2 coils of wire and they have turns in them. And you have one that's called the primary and one that's called the secondary. Now, the efficiency between the primary and secondary, they're 100% efficient. So we need to know that transformers are 100% efficient. So what does this mean? The power going in the primary coil in watts is equal to the power in the secondary coil. We don't lose any energy. And we know that power, remember, P equals I times V. And this essentially says the current going into the first coil or primary coil times the voltage in that first or primary coil is equal to the current in the secondary coil over here times the voltage in the secondary coil, because power 1 is equal to power 2. We don't lose any power. Now they've given us that the current in the first coil was 660 amps. And we know that if we multiply that by the voltage in the first coil, which was 400,000 volts, that is equal apparently to our missing unknown ampage in the secondary coil times 11,000. So can you rearrange this to find that? Well, all you can simply do is you can multiply 660 times that by 400,000 and you're going to get the power in watts. So 264 million watts is produced in both coils. So I times V equals the power, and this also must equal 264 million. Now, just remember you have your triangle, which is P over IV. So if I want to find the current, which is the amps, I just do the power divided by the volts. So I'm going to do 264 million over 11,000, and that is going to give me, oopsie, put it wrong in my calculator. That's going to give me 24,000 amps of current coming out in the secondary coil. Booyah. Awesome. And there we go. That's going to be 3 marks, 3 lovely marks. So you do need to know I1 times V1 is equal to I2 times V2. You then just substitute the numbers, whack them in, and then divide, find the answer, divide that by that to get that. And that's the triangle that helps me with rearranging. All right, let's move on. Okie dokie, 3.3. Why is the current in each street lamp less than the current in the secondary coil in transformer Y? So why is the current in each street lamp less than the current in the secondary coil in transformer Y? So now we're going to read these. So what it's saying is, remember we had 24,000, we just worked it out, 24,000 amps of current came out the transformer, but when it goes into the light bulbs or the lights in the street, they don't each get 24,000. Let's just take a little bit of a look back at that diagram. There it is. There's the diagram. Have a look here. These are arranged in parallel. Well, obviously, if they were in series, they get dimmer with every street lamp you added, which would be no good. We don't really arrange a lot of things in series. So current is used in the cables between Y and each street lamp. Is it because we lose current? No, current's not used by the cables. Some of the current is dissipated to the surroundings. Is current dissipated? We don't get electricity going through the air. We get heat dissipated. So they're trying to trick you here. Heat is dissipated to the surroundings, but that's not the current. The cables between Y and the street lamps have electrical resistance. This is true. All cables will have electrical resistance. So again, they're trying to get you here, but that's not the reason. The reason is the street lamps are connected in parallel. And so just to show you, if you have 24,000 amps and that's coming down a circuit, and then that circuit branches like this to some lights, then that current is going to divide between the branches. And that is one of the rules of parallel circuits. The beauty is that when it comes back together to return to the supply, it will go back to being 24,000 volts. Now, it might be that 14,000 goes there, 10,000 goes there, or it might divide evenly 12,000 and 12,000. It depends on the resistance of that lamp and the cables in it as to how much current is drawn into each lamp. But essentially in a parallel circuit, current divides between the branches. So the street lamps are connected in parallel. That is why the current in the lamp will be less than the total current that came out the transformer. And there's your answer for that. All right. Okay, let's have a close look at this street lamp. So 3.4, figure 8 shows the top of the street lamp. We've got a light sensor. See that little ball? You might even spot them on street lamps on your street. And you've got the lamp there. The light sensor detects if it is day or night. Figure 9 shows part of the circuit in the light sensor. So inside that little plastic ball on the street lamp this is part of that circuit. And we've got a resistor labeled R, and then we've got this symbol. Hopefully you know what that is. You should revise and learn all your symbols. Explain what happens to the potential difference across resistor R as light intensity increases. Hopefully you know, using the wrong pen there. Sorry guys, 1 secondo. Hopefully you know that this symbol is for a resistor. And then if you have 2 arrows going towards it, they represent rays of light, sunlight, or just light hitting the resistor. This is known as an LDR, a light dependent resistor. And you also have to know off by heart the graph that goes with a light dependent resistor. You have to know the one for a thermistor as well. And it has light on the X axis, and it has resistance in ohms on the Y axis. and the shape of the graph is like that. What this tells you is that as we increase the light on that resistor, the resistance goes down. If we decrease the light, the resistance goes up. So let's see what our question is saying. Explain what happens to the PD, the voltage or potential difference across R as the light intensity decreases. So as we get less light, what's going to happen on the LDR? Well, I can tell you what's going to happen on the LDR. As there's less light, so less light means resistance increases on the LDR, the light dependent resistor. So the resistance on that has increased. What value in electricity do you know has a relationship, an inverse proportional relationship with resistance? And hopefully you know it's current. As you increase resistance, current goes down. If you reduce the resistance, currents goes up. They have like an inverse relationship. So we can say, so current in the LDR decreases. So we're going to have less amps going across the LDR. Now, if we have less amps going across the LDR, we're going to have less amps going across R. And so the voltage or PD, potential difference, decreases across R. Now, even if you find that a very difficult concept to understand, some of this is memory recall. So you've got no excuse not to know that that symbol is an LDR because you should have made a revision cards and learned that. And there's also two sketches, one with light here and resistance there for the LDR, and then one for the thermistor. The thermistor kind of like, yeah, the thermistor looks like that or roughly like that and has exactly the same graph, but you've got temp there and resistance there. You need to know those shapes off by heart. There's some other sketches as well you need to know for this topic. But if you know that off by heart, then you'd know that as light intensity decreases, resistance increases. So you definitely get that mark. And then if you know the relationship between resistance and current, you definitely get 2 out of 3. And then it's kind of a 50-50 as to what happens to the potential difference across our as in from memory recall. So you should be able to get 2 out of 3 on that at least. Right, let's zing on. That was pretty hard, but we have followed with a lovely maths question, and these maths questions always get us marks in physics. They're absolutely beautiful. Okay, 3.5. When the current in resistor R is 20 milliamps, what does that mean? Think about that little m. It means milli, it means 20 over 1,000 amps. Okay, now that is 0.02. And already, bang, smack, I haven't even read the question. We just picked up a mark. Boom. So when the current, yeah, what do we want to do? The power transferred by resistor R is 6 watts. What does the W stand for? Well, that's watts, which is the unit of power. And in your equation sheet, you're looking at P there. Calculate the resistance of R. R is measured in ohms, but on the equation sheet, resistance is represented by an R. And over here, the current is going to be I. So when you bust to your physics equation sheet, and this is 4 marks, you're going to find this equation, and this will get you it all in one go. But there is another way to do it if you really messed up and you didn't use this equation. So I'll show you both ways. So power is equal to I squared over R. We want R. We want R. So we're going to divide both sides by I squared. We're going to get P over I squared equals R. We just need to smash the numbers in. So the arrangement of that is going to get you a second mark. We need to smash the numbers in. So, where am I? Where am I? Where am I? Here I am. So we're going to go 6 watts divided by 0.02, which is 20 over 1,000. If you forgot to do that, you can still get 4 marks. If you missed out the milliamps, you just did it as amps. So if you did it as 20 squared, that's fine. So 6 divided by 0.02 squared. So we're going to go 6 divided by 0.02 squared, and that equals 15,000. So you're going to get a mark here for squaring that, bashing that, and doing that. So that's 4 beautiful marks. Now, there is one other way here, guys. We could have done, if you didn't use that equation, because maybe you just are averse to it, you could use the P over P equals I times V. So we could go 6 is equal to 0.02 times V. So I could go 6 over 0.02, and that would give me 300 volts. Now, they haven't asked for volts, but this here would get me 2 marks. Now, I could then take this equation over to the V equals I times R and do V over I equals R. And my voltage was 300, and I could divide that by 0.02, and that would also give me 15,000. So there's more than one way to skin a cat in physics. There's more than one route. Personally, I'd use the P equals I squared times R, but if you're not comfortable with that, you can combine these two equations to come to the same answer. Okay, let's zing on to question 4. So we have a scientist investigated a sample of a radioactive material to determine if it would be suitable for medical use. 4.1, the method, results, and conclusions of the scientist need to be checked by other scientists before the results of the investigation are published. What name's given to this? So when you're a scientist and you found something out or you've done an experiment, you have to publish before it's published, you have to share your information with other people in your field. And this is known as peer, which means people also in your field, peer review. You need to know that off by heart is when scientists share their results with other scientists who check that they did it correctly. It's a way of science as a field not making stupid claims. So someone can't say, oh, I've found the cure for cancer and say, this is going to cure cancer and I'm going to sell it for £1 million. If they're a proper scientist, they have to release their information and their experimental data so other scientists can look at it and check they did it correctly. Okay, 4.2. There is an increased risk of cancer if the scientist is irradiated by nuclear radiation. What property of nuclear radiation causes increased cancer risk? And this is just a one-word answer. Why is radiation dangerous? Dangerous? I can't speak today. It is ionizing. Okay, and what does ionizing mean? Well, you know from chemistry, ions are atoms that have lost an electron or gained an electron. In this case, radiation causes atoms to lose an electron and become ionized. So if you have a bit of radiation and it smashes into an atom, remember we have electrons going around atoms in orbitals. If the radiation smashes into an atom, it can knock an electron off, and that atom can then gain a positive charge because it's lost some negativity. It's become an ion. And then through a series of complex reactions, that if that happens to an atom within your DNA, it can cause a gene mutation, a change in a gene, which can eventually lead to cancer. So ionizing radiation is dangerous. Superbulous. Right, let me just zing to the next part of this question. Right, 4.3. The activity of a radioactive source is the rate at which the nuclei of the source decay. What is the unit for the activity of a radioactive source? Again, this is just one you guys have to know off by heart. No excuses. It's called becquerels. You don't have to know that off by heart. You can just do capital B, baby Q. Becquerels. And that is how we measure activity of a radioactive source. However, it's quite difficult to measure activity, and I'll come on to that with this next question. 4.4, the scientist placed a radiation detector near the sample and measured the count rate. Sometimes they'll ask you the name of the radiation detector, this thing here, and it's called a GM tube. You can call it a Geiger counter or a Geiger-Muller tube. But it's a GM tube. I don't know why I did a tuber. Tuber's like something a potato grows. Never mind. So it's a GM tube. Anyhow, that's not the question. So why am I waffling? Explain why the count rate is less than the activity. So if they grab this Geiger-Muller tube, what a Geiger-Muller tube, let's say this is my radioactive sample over here. This is my oh my gosh, I can't spell, radioactive sample here. That is going to be giving out radiation like this. Boop, 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 boop. So it's giving out radiation. Now, if you imagine this is a sphere, a three-dimensional object, it's giving out radiation in every direction and in every plane. The Geiger-Müller tube can only record radiation that gets in and smashes to the back of the tube and is detected. So we call this the count rate, the amount of particles entering the Geiger-Müller tube per second. And that's always going to be less than the activity, the becquerels, which is the total amount of radiation per second leaving the radioactive sample. So it just can't measure the radiation in all directions. So the GM, and you don't need to use this, the GM tube can only measure radioactive particles that enter the tube. So it can only measure the radiation or the radioactive particles that enter the tube. Activity, I can't spell activity, activity is the total radiation per second leaving the sample in every direction. I swear I've worded that terribly, but essentially the radiation detector can only detect radioactive particles that hit it. It can't detect all the particles going off in every direction, and that is why our count rate is less than becquerels. You might say, doesn't that make count rate useless then? It doesn't, because if I have two samples, X and Y, the count rate will still be higher in the more active sample because more radiation will be entering the tube per second. So it's still a great way of telling whether there's a lot of radiation coming from something or a little. It's just not very good at giving you the actual amount of radiation leaving every second. Okay, enough of my whiffle, waffle, whiffle, waffle, waffle. Let's move on. We're on 4.5. So the scientists recorded the count rate from the sample with a radiation detector at different distances from the sample. This shows the results. Distance between the sample and the detector, 2 centimeters, we had a 300 count rate. At 5 centimeters, we had a 24 count rate. At 10 centimeters, we had a 0 count rate. Which type of radiation was emitted by the sample? Do you know your 3 types of radiation, people? You've got 3 types of radiation. We got alpha, we got beta, and we got, I can never draw this one, we got like gamma. It's like a weird Y thing. Okay, alpha is very ionizing, so quite dangerous because it's heavy, it knocks electrons off of things, but it's got rubbish penetration. It's blocked by air. That's why it's in a smoke alarm. Thick smoke or dense air will block it. In fact, beta can go through a little bit more air, but it's blocked by thin tin foil. Think of that metal foil that you wrap your sandwiches in. And then gamma is only really stopped by thick substances like 2 or 3 foot of concrete or a couple of centimeters of lead. Or so gamma is only blocked by dense metals like lead. So what about this radiation? Well, it got through 2 centimeters of air, all right. Got through 5 centimeters. It couldn't get through more than 10 centimeters of air. So think about that. That's not very long at all. 10 centimeters, about the size of your hand. So it can't travel very far in the air. This has to be alpha radiation. So this is alpha radiation as it has low penetration and so absorbed by air. If it was beta or gamma, it would get through the air. It would certainly travel a lot further through the air. So the answer here is alpha because of the low penetration, or it's absorbed by air. Right. Oh my gosh, this is the question that just keeps on giving. 4.6. The scientists moved the detector closer to the sample, gosh, and started a stopwatch. The scientists measured the count rate from the sample at different times. This shows the results. We've got minute, 0, 30, 60. Count rate in seconds, 1,568. And then we've got a missing one. They're obviously going to ask us for that. And then at 60, it was 98. The scientists realized that 30 minutes is a whole number of half-lives. That's a nice realization. Calculate X. So you might be like, where do I start? Well, look, they've given you the starting count rate. That's the starting radioactivity. Now, they do this with activity sometimes or count rate. They're 2 different measurements of radiation. Both are good. And that's the end activity at the end of the test. So if we know that, half-life is the time taken for the count rate to half. So let's find out what the half-life is of this sample. So we go 1568. We half it by dividing by 2 in our calculator. 1568 divided by 2, and we get 784. That is one half-life. See that arrow? That represents one half-life. The reason why I draw this out and don't do this in my head with my fingers is because you will get it wrong. You'll overestimate the number of half-lives. So then 784 divided by 2 is 392. Okay. And then let's keep dividing. What's 392 divided by 2 is 196. Let's keep dividing. 196 divided by 2 is 98. Look what we've ended up with. We've ended up with the numbers. How many half-lives took place? 1, 2, 3, 4. So we can say there were 4 half-lives. There were 4. You would have already got a mark from your working out, but there were 4 half-lives, and that's going to get us a mark, right? And you could also identify how long was one half-life. Well, it halved 4 times in 60 minutes. So a half-life in this terms, not all half-lives, they're all different, but for this one is 15 minutes. So we've calculated that the half-life is 15 minutes. Okay, it's halving every 15 minutes. So if it started at 1568, what would it be after 30 minutes? So this would be the first 15. And then after the second 15 minutes, which makes 30, it's going to be 392. So that is what it would have reached. It would have halved twice in this time, and so be 392. You could say 2 half lives have passed in 30 minutes. Beautiful. Right, that's all the marks there. Okay, oh my days, does this question ever end? Oh yeah, it does. 11 marks only. The scientist had a second sample of the radioactive material. The scientist made appropriate measurements, then calculated the half-life of each sample. Why was the half-life calculated from the second sample slightly different? So what we're saying is instead of 15 minutes, it was like 15 minutes and 10 seconds or 16 minutes. It was only slightly different from the half-life calculated from the first sample. Radioactive decay is a random process. This is true, and I'm going with that as the answer. The count rate from the radioactive sample is predictable. The samples were at different temperatures. Temperature does not affect half-life, and the size of each sample was different. The size of the sample does not affect half-life. You could have a speck on your hand, or you could have a football stadium's worth of radioactive material. If they're the same thing, the same element, they will have the same half-life. So it's the fact that it's a random process. We don't know from any 1 second when a radioactive particle is going to, or an unstable nuclei is going to break down. Right. We're on to question 5, peeps. Let's go. Okay. Figure 10 shows a child's toy. A child pushes down the toy to compress the spring. The spring then launches into the air. Woo! The student measured the maximum height reached by the toy. The student placed a vertical ruler near the toy. Okay, here's our ruler. And observed the height reached by the toy. The student repeated the experiment, observing from a different position. Here's position B. They're looking there. Figure 11 shows the toy at its maximum height and the 2 positions of the student. Observing the toy from B instead of A affected the measurement reached by the toy. Explain how. Which one is more accurate to you? The student looking there or the student looking here? Which one is the student going to get a more accurate measurement? You've guessed it. It is position B. Position B will be a more accurate measurement as it is at, or the toy is at eye level. So, I mean, you couldn't really do that unless you had a couple of practice runs and worked out roughly where the toy is going to go, so where to put your eyes. That's why the student has adjusted their experiment. But yeah, beautiful, beautiful, beautiful. 1 mark for B is more accurate, and 1 for the reason because he's measuring the toy at eye level. Right, let's zing on, Tom. Let's get this done. We're nearly there as well, so let's go, let's go. 5.2, the greatest height reached by the toy was 64 centimeters. So I've been given a distance or height, they've told me. The gravitational potential energy of the toy. Oh, great. I've got energy. And then I've got GFS, gravitational field strength. Calculate the mass of the toy. Use the sheet and two significant figures. Beautiful. Right. On your sheet, there is a equation, which is GPE, gravitational potential energy, is equal to mass times height times GFS, gravitational field strength. Now they don't actually they don't put the G there, they put potential energy. So you'll see it slightly different on your sheet, but this is the equation you want to use. So what we want to do here, guys, is rearrange that, and we can leave M on its own. We want the mass. That is what you need to circle in the question, what you're actually trying to calculate. So we want the mass on its own over here. So we're going to divide GPE by height and GFS. So when you want to get rid of two things that are being times, you just divide them by both sides. So we're going to get height times GFS. GPE over height times GFS equals M, and that is going to pick you up a mark. So you're going to get a mark for selecting the right equation. You'll probably get a mark just for selecting that equation. You get a mark for rearranging the equation. We're now going to get a mark because in science, we measure height, distance, any sort of length we measure in meters, especially in physics. You don't use centimeters. So we need to do 64 over 100, and that's going to give me my height, which is going to be 0.64. My GPE is 0.049. That is totally correct. You don't use kilojoules, we use joules. So 0.049 over 0.64 times 9.8. You want to bracket these if you're doing this in your calculator, and then that is going to give us our answer. And then we want two significant figures. So we've already scored 2 marks there, one for the conversion, and putting this in there is 3, and then we want one for two significant figures. So let's go 0.04. Oh, you turn the calculator on, Tom. 0.049. There's no way I'm doing this one in my head. Divided by 0.64 times 9.8, close brackets, and that equals 7.812 times 10 to the minus 3. 7.812 times 10 to the minus 3. So three significant figures, 7.81 times 10 to the minus 3. You can go 0.00781. Ah, it said 2 sig. What a wally. Right, this said two significant figures. I've done it to 3. I'm used to going to 3 in A level. So what we're going to do here, we're looking at 7.8 or 0.0007.8. So 7.8 times 10 to the minus 3. So 1 mark for the equation, 1 mark for the rearrangement, 1 mark for the conversion of the height, 1 mark for banging it all in the equation together, and then 1 mark for rounding to 2 sigs. Okay, final bit. When the temperature launches the toy into the air, sorry, when the spring launches the toy into air, the air temperature increases. Explain why the child's toy on its own is not a closed system. So it's not a closed system because energy is being dissipated as heat to the environment. In a closed system, the energy stays in the system. So if it was a closed system, the toy, the energy would stay in the toy and it wouldn't be transferred to the environment. So that's what we're getting across there, and that is worth 2 marks. Bosh, bish, bash. Now let's move on. So this looks like it could be the final question. So for this combined science paper, so 6 shows a device that uses a mug of hot coffee to turn a wheel. I mean, have you ever seen such a pointless device? So we've got hot coffee. The heat from this is somehow doing something to this air chamber, to this piston that's turning a wheel. I mean, yeah. Okay, it's a fun device, but its use is pretty dumb. 6.1, the hot coffee increases the temperature of the air in the chamber. I guess it's good for explaining stuff and showing how various types of engines and things can work and devices. So I shouldn't say it's dumb. A hot coffee increases the temperature of the air in the chamber. Explain how the pressure in the chamber changes. Right. This is one of these good old pressure ones. You need to know this off by heart, guys. They always ask this, whether it's combined science or the physics separate paper. Pressure is equal to force divided by area. And we need to always think of pressure in those terms. Force over an area. But then we combine that with our knowledge of particle theory. So explain how the pressure in the chamber changes. So what's going to happen to the particles in the chamber? So the particles, I'm going to do the long version. The particles gain Ke. Hopefully, you know that means kinetic energy. More collisions with each other because they've gained kinetic energy, and the walls, whoops, of the chamber. And whenever you're going to say more collisions, you generally want to say more frequent. So more frequent collisions with each other in the walls of the chamber. This means a greater force is exerted over the walls or the area of the walls. Notice how I've worked area in because it's in my equation, area of the walls, uh, making a greater pressure. Boom. So what we're doing here, guys, we're saying particles gain kinetic energy, more frequent collisions. More collisions with the walls means more force over an area, increasing the pressure. Essentially, they didn't say whether the pressure went up or down. So you get 1 mark for saying the pressure went up. And then you could just say because collisions mean more force over the area of the walls. Okay. Lovely, jubbly. 3 beautiful marks. Make sure you learn that one. They love to ask about pressure and how temperature increases pressure. So kinetic energy, more particles colliding with the walls of the container, creating a greater force over the area, F over A, which equals P. You're going to get a bigger pressure. Right. We're nearly done, nearly done, nearly done. What are we on? 6.2. Okay, for the device to work, the air in the chamber must increase in temperature quickly. Explain why the bottom of the air chamber is made of metal rather than plastic. So hopefully you know metal is a conductor. Now they don't want this next bit. This is just me being an idiot. Metal is a conductor, has free electrons. Actually, I'm not even going to bother with that. Metal is a conductor, um, transfers energy faster than plastic, which is an insulator. So yeah, metal is a better conductor than plastic. Um, Plastic is a better insulator than metal, so heat energy is transferred faster through the conductor. And it's because they have delocalized electrons, which I was going to start to waffle about, and then I realized there's no point. 6.3, the mass of the air in the chamber is constant, so the mass doesn't change. What property of air allows a small change in internal energy to cause a large temperature change in the air? So we've got something called specific heat capacity. Now, that is the energy Q equals M mass times C times delta T. And that is the equation for specific heat capacity. Now, what property of air allows a small internal energy to cause a large temperature change? So if the mass is the same, but you've got a low specific heat capacity, then you're going to get a large change in internal energy. So what we have is a low specific heat capacity. I don't think my use of the equation was a very good explanation. Essentially, specific heat capacity is the amount of energy required to change the temperature of a substance, raise it by 1 degree. So if you think we have a very low C and the mass is the same, you won't need much of, in order to raise the temperature by 1 degree, you won't need a big Q. You don't need a lot of energy to change the temperature. Okay, whereas something like water, you need 4.18 joules. Yeah, per kilo to raise the temperature by 1 degree, or per gram, sorry, to raise the temperature by 1 degree. I'm just waffling now. But essentially, specific heat capacity is a measure of how hard it is to change the temperature of a substance. So if you have a low specific heat capacity, it's very easy to change the temperature of a substance. If you compare water to air, think about the Earth on a 35-degree day where it's really hot outside in a lovely summer's day, the air temperature goes really high. And then in the winter, when the air temperature drops to like -2, but if you went and jumped in the beach, in the water at the beach, the water always feels blooming cold. And that's because it takes a lot of energy to change the temperature of the water, whereas air, which has a small specific heat capacity, is very easy to change. I'm double waffling. Let's get on and finish this paper, Tom. Okay, 6.4, the changes in the pressure in the air chamber cause the wheel to turn, suggest one way to increase the speed at which the wheel turns. Okay, so let's just increase the temperature of coffee. If it's hotter, you're going to get a bigger increase in the pressure, blah, blah, blah. That will increase the, yeah, hotter the coffee, the more the particles move, greater collisions, more force over area, greater pressure, faster the wheel's going to turn. Right. Oh my gosh. Oh my gosh. Last question, people. 6 marks. We need to work out the final temperature of the coffee fee. Coffee fee. Right. As Mr. Trump would say. Uh, So what have we got going on here? We've got the temperature of the coffee decreases as the device is used. We've got an initial temperature of 76 degrees. We've got an internal, the temperature of the coffee went down by 15,000 kilojoules. We've got a density of the coffee. Lovely. We've got the volume of the coffee. Ooh, DMV. That means density equals mass over volume from your equation sheet. That means we're going to need that equation because we've located D and we've located V. Now we're already thinking we've got energy and we've got temperature, and it says initial temperature. So we're going to have the change in temperature. So it looks like specific heat capacity, and we're given the specific heat capacity. So yeah, that's the little C thing. Calculate the final. So you're going to need these two equations. We're going to need D equals M over V from the equation sheet. And we're going to use, I use Q as energy, by the way. Q equals mass times specific heat capacity times the delta change. Okay, in temperature. I need to find the change in temperature, then add it to 76. I would say, have a go at this equation. Bob. Right. Where am I going to start? You want to start with the equation. Do I start with the density equation or the specific heat capacity one? You want to start with the equation which you have all the elements to work out anything missing from. And with this one, we have D and V, so I can work out M. If I do specific heat capacity, I want to work out triangle T or delta T, but I don't have M, so I can't work it out. So I need to do the density one first. So density of the coffee is 1.1 times 10 to the 3 kilograms per meter cubed. Now, I've also got the volume of the coffee as 1.2. So if I do density, so I'm going to do D times V, and that equals mass. So that's going to give me a mark. And I'm going to carry that out now. 1.9 times 10 to the -4. And we're going to get volume times density. We're going to give ourselves 1.1 times 10 to the 3 multiplied by 1.9 times 10 to the -4. And that is going to give us 0.209 kg. Now, sometimes this one's done in grams, but we can see here with the specific heat capacity, it's 4,200 joules per kilogram, and the density is, we're operating with the kilograms here, peeps. So our mass is in kilograms for this next one. So the next bit is we have 15,000 kilojoules. That is Q or E, depending on how you write the equation. Now that is 15,000. So you're going to gain a mark from calculating the mass. So that's 2 for using the density. Going to get 1 mark for your conversion of 15 kilojoules to 15,000 joules. And that is equal to M, which was our mass, 0.209, times specific heat capacity of 4,200 times delta T. Sometimes in AQA they write delta T like that. I I can't stand that, but there we go. Right, let's do 15,000 divide. We want to bring these over and leave the delta t on its own. So we're going to do 15,000 divided by 0.209 times 4,200, bracket that baby, and then equals delta t. Okay, and that is going to give us another couple of marks. So we're going to be up to 5 marks if we get this right. 15,000 divided by bracket 0.209 times 4,200, close brackets. We're going to get 17.088. Now that is the temperature change. We've got to add that to 76. So we're going to go 76 plus our answer of 17.089 or 88, and that's going to give us our final one. So 76 equals 93. You could go 0.1. I don't know how many decimwessies they want it to, but there we go. That's going to get you 6 marks, guys. All right, smash the like button, hit the bell, subscribe, people. Let's get to the marks and get those exams done.
You're still here? It's over.